Well, we're back, and today we are going to make a third try at calculating the stability of the hydride anion, and we'll hope the third time is lucky. And we're also going to talk a little bit today about the orbital philosophy and exactly what that means when it comes to atoms and molecules. Chemists love orbitals much more than they love wave functions, for the reasons that we'll see. Okay, we first had the calculation with perturbation theory. We found that the hydride anion was unstable, the energy was -3/8, and that's not favorable compared to a hydrogen atom and an electron at infinity. And then we said, what if we go ahead and optimize the radius by changing the exponent? And we could do that. We could get a formula for that. We did it, and unfortunately, it's still not stable. That means that the true wave function has a different form than that. That's all that means. Or it might mean, if we didn't have experiment, it might mean the hydrogen anion is unstable. That could be true. Some anions, like neon, are unstable. How can we improve our guess? That's the thing. So here's the thing. We had the same value of the exponent, whether we picked the just the Bohr radius, or whether we picked, so in atomic units it's just 1, or whether we picked this zeta. We had the same value for both electrons. And on average, that's got to be true, because the two electrons are indistinguishable. But at any instant that might not be true, because suppose one electron is nearer to the nucleus than the other one, then this electron is more like a hydrogen atom electron, and this electron is kind of a funny one because most of the attractive force is temporarily shielded, and so it could in principle have a widely different exponent than the first one. Therefore, what we might try to do is we might try, instead of having the same exponent, e to the zeta r1, e to the zeta r2, we could have e to the minus zeta 1 r1, e to the minus zeta 2 r2. And then we could try that. Unfortunately, we can't do that alone, because if we did that, then we'd be saying that the electrons are distinguishable, because one would always be nearer than the other one, and in fact they're the same. And so what we have to do is we have to pick a guess now at a wave function that on slide 470 here is symmetrical. I have a normalization constant out in front, what I've just called n, and then I have e to the zeta 1, e to the minus zeta 1 r1, e to the minus zeta 2 r2, plus the other way round, e to the minus zeta 2 r1, e to the minus zeta 1 r2, and then divide by 2, just so that when zeta 1 is equal to zeta 2, it's equal to the one we tried before. And that way we can check our previous answers. Now, n, we have to have the normalization right, because if we don't normalize the wave function, then the energies come out haywire, because we have this factor of n squared that shouldn't be there. Therefore, the first thing we have to do is figure out what that value of n should be. The integrals here become epically messy, and they take a long time to do. And you have to be extremely careful when you do them, because if you make any kind of goof, even a minor one, everything is wrecked. You have to be very meticulous to keep track of everything, and it can get to be extremely tedious if you've got a lot of terms. But I will have gone through, and I think I've been very careful, and I've written out in full what the answer should be at each stage and given you the rationale. I don't want to go through integrating by parts over and over and over again, but you should be able to look up antiderivatives for many of these once you see how to do them. Okay, here's our assignment then. We have to obtain an expectation value expression for the energy of the hydride anion, and it should be an energy functional which depends on zeta 1 and zeta 2. And that could be a very messy formula. We don't know exactly how that's going to come out. Then what we have to do is we have to find the optimum energy by choosing the correct value of zeta 1 and zeta 2. And they should be different. And of course, because either one of them could be the inside one, there are two equal solutions. There's one where zeta 1 is small and zeta 2 is big, and there's an identical solution where zeta 2 is small and zeta 1 is big. And that means that the surface, two-dimensional surface of energy versus zeta 1 and zeta 2 has two equal minima. And that can be a little bit tricky sometimes to find the correct value. So you may want to, if you're trying to search, for example, always make one of them like 2 bigger than 1, so that you don't actually fumble around and fall into more than one minimum. And in doing this, what we have is an intuitive physical picture that suggests that this might be a better type of guess than just picking the same value, having the same kind of orbital at all times. So of course this is more flexible than the other one, because when we pick zeta 1 equals zeta 2, we get the other one, so we cannot possibly do worse than we got before, and we know what the answer was before for zeta, so we have a good guess of where to start when we start looking around on the energy landscape. But let's go ahead and see if we strike out or if we can at least get on base. First, let's calculate the normalization constant, and let's do it in 2 stages. What I've first done here is put in the integral just over R1, and then I've put in the sine theta 1, d phi 1, and all that stuff, R squared. And then we have to put in that messy thing times itself, which gives 4 terms, and then we have to integrate them all up. And what we get here is 4 pi n squared over 16, and then 3 terms in zeta that all have exponentials in the top, and cubic terms, zeta 1 cubed, zeta 2 cubed, and zeta 1 plus zeta 2 quantity cubed in the bottom. And that comes from just doing the integral by parts. There's no magic there. This is pretty messy, but it's not too bad. But now what we have to do is we have to integrate this thing over R2 in order to get the normalization constant. And so I've shown that here on slide 473. We're integrating I of R1, which is the integral with respect to R1, over R2. We have to put in the R squared, the theta, the phi, and so on. We end up now with 4 pi squared n squared times 1 over 32 zeta 1 cubed, zeta 2 cubed, plus 2 over quantity zeta 1 plus zeta 2 to the 6th. And therefore, we can solve that for n. We want that integral to be 1, because that's what normalization means. And therefore, n has to be 1 over all that other stuff. Let's check. Let's put in zeta 1 equals zeta 2. We know from before, when we did the integral just with a single value of the parameter zeta, that the normalization was zeta cubed over pi. And of course, when zeta is 1, the normalization is just 1 over pi for a 2-electron wave function. Let's put that in, and we put it in, and we have to do a little bit of math here. We have 1 over 4 pi square root of 32 zeta to the 6th plus 2 over 2 zeta to the 6th. That's 1 over 32 plus 2 over 64. That's 1 over 16. Magically, the square root of 16 is 4. That gets rid of the 4. And the zeta, since it's in the denominator, and we take the square root of zeta to the 6th, comes up to the top, and we get zeta cubed over pi. That's a good thing to be able to do when you're trying to generalize something you've previously done. In fact, that's what scientists always do. When they're proposing something new, some extension of a theory, some extension to an experiment, whatever it might be. They always want to have one foot on land. You don't want to just jump into some kind of unknown sea of knowledge where you don't have any kind of compass for where you're going. You want to always be able to check that what you've done isn't wrong and that it makes sense and it reduces to the previous case whenever you can. And we're going to do that throughout this calculation, because although these integrals to calculate n are a little bit tedious and maybe seem extremely hard if you aren't used to doing that type of thing, they're nothing compared to what's coming up. For simplicity, and so I can fit the darn formulas on these slides, I'm going to leave n out until the very end when I actually need it to calculate the energy. I'm just going to leave it out and calculate things without it. The one electron, so the electron 1 and electron 2, kinetic and potential energy terms are just as they were before. And we're going to calculate them just like we did before. We're going to have to take the derivative and so forth and so on. And we can take the derivative of an exponential. That's not a big deal. And the factor of 1/4 in this integral that I've written here on slide 475, the factor of 1/4 comes from the fact that we defined our wave function to be the combination divided by 2. And then the factor of 4 pi comes from doing the angular parts of the integral, which just is 2 pi times 2 for the phi and for the theta part. And then the rest of it is what we have to do, which is the integral now over r1 squared psi star, without the 2 because we took that out, h1 psi. And we're just going to do the first electron because the second electron has exactly the same kinetic and potential energy, and therefore it has exactly the same total energy. It would just be switching the indices, and so we don't want to do it over. Why bother with that? Now we integrate by parts. And we integrate by parts over and over because we've got these 4 terms and then we've got r1 squared, and when we integrate by parts we have to do it a couple of times to get rid of the r1 squared, and boy do we end up with this mess here on slide 476. The integral with respect to r1 of this sandwich with the Hamiltonian is this very messy thing with 8 zeta 1 squared, zeta 2 squared times zeta 1 plus zeta 2 quantity cubed, and then a bunch of other terms with polynomials in zeta 1 and zeta 2. And so I've written it as this big stack of things, and you have to keep track of the minus signs and so forth and be quite careful here. In a very quiet room, with a piece of butcher paper, you now take this formula and you have to integrate it carefully over R2 without making any mistakes. And the most important thing to do when you're doing this type of work is don't write out the whole thing. Just say, let y equals this whole thing, and then carry it along. Don't keep rewriting out the whole formula. You'll go crazy. Always use a shorthand. But then when you have to put everything back in the end, you have to be extremely careful when you substitute things back in that you don't make a goof. Let's integrate over R2, and then we end up with a 4 pi for the angular part because there's no angular dependence to this function that we had after integrating over R1. We just had the variable R2, so the other part's 4 pi. And we end up with pi squared over 8. And then this functional in zeta 1, zeta 2, and of course there's no r left, no r1, no r2 because we integrated them out. Great. Finally, we have to then now put in our normalization constant, and we end up with this very messy thing at the bottom of slide 477. So messy it'll it'll barely fit on the slide, and it may actually be hard to read for all I know. You may have to stare at it quite a while, even if you have a big monitor. But we have this formula that now tells us what the energy of electron 1 separately with this particular form of the wave function interacting with the nucleus is. We have 1/12 times 3 minus then this huge polynomial in zeta, and then there are some rational functions in zeta. Rational function is p of zeta divided by q of zeta, and you can see the last two terms are of that form. So we have some regular polynomials and some rational functions here in zeta 1 and zeta 2. Electron 2 then has the same formula as electron 1, which just swap all the indices. Wherever you see 2, put 1. Wherever you see 1, put 2, and you better get the same answer. If you don't get the same answer when you did that, that means you made a mistake in the integral. And if we put in zeta 1 equals zeta 2 equals 1, that was the very first thing we did, then we should have a hydrogen atom orbital, and we should have the energy as minus 1/2 Hartree. And in fact, you can check that. If you take this very messy formula and you put in 1, great, because 1 to the 6th is still 1, so it's pretty easy to do. And you can watch everything come out in the wash, and you get minus 1/2. Good. That's a very good check, because that doesn't mean that we're correct. It just means that we aren't wrong, that we haven't made a mistake for sure, but it doesn't mean that we're for sure correct either. We might still be wrong, have the wrong formula that reduces to the right case, but usually not. Two if it reduces to the right case, you're on the right track. Now, to complete the energy functional, we have to take the two 1 electron terms. Good, we can add those up. And then we need the repulsion term. We need the integral of 1 over R12 with this bigger expanded wave function. And remember, the 1 over R12, in order to do that at all, we needed the law of cosines. And so we're going to have that again. And recall that what happened there is we had the integral separate into two cases, depending whether R1 was bigger than R2 or R1 was less than R2. We either got 2 over R1 or 2 over R2, and then we had to separate the final integral into the separate cases. So we're going to have to do that again here, and everything's going to follow through exactly as it did before. The only difference is it's going to take a lot more effort, because just having these two terms, then we get all these cross terms, and then we have to deal with each one of them separately. If we're clever, though, we can save some work, because we did do this before with R12 with the same thing on either side. So that part's not too bad. We could kind of crib our work. We have cliff notes for that. And then we've got these asymmetrical ones that we haven't done before and might come out to be a different thing. Here's the repulsion integral written out over R2, theta 2, and phi 2 here. And recall that the theta part is the only part that has a dependence that's different from before, and that came from the law of cosines. That's just figuring out the distance between the two electrons as we integrate theta. And I'm not going to go through changing variables for cos theta equals x here, but that's exactly what we do. If you want, you can go back and review that, and we get exactly the same thing. And then we end up with these two terms to do 2 pi times 2 over R1. The first integral is dr2 r squared psi squared plus 2, and the second integral is dr2 just r2, because we had a 1 over r2 for that one. And that second integral has the limits from r1 to infinity. The first integral has the limits from 0 to r1. And we get two different cases because we had the absolute value of R2 minus R1 when we got the antiderivative. And it makes perfect sense that we have the absolute value in there for the antiderivative, because it's the absolute value of R2 minus R1 that's telling us how far the darn electrons are apart. Of course we expect that to come out when we do the calculation. I'm going to have to separate now the two integrals into separate calculations because it's just too huge. Here on slide 480 is the first of them. The first integral, 2 over R1, the integral from 0 to R1 of this thing. We have to expand it all out and we end up with quite a mess. Good thing we don't put in the n. So we n squared over 8R1 e to the minus 2R1 times zeta 1 plus zeta 2 times this huge thing, rational function in zeta 1, zeta 2 that takes up the rest of the slide here. And you can see it's of much the same form as the other one. We have zeta 1 cubed, zeta 2 cubed, and then we have zeta 1 plus zeta 2 quantity cubed, and that again comes from integrating by parts. That's what we get. Okay, now we've got to do the second integral, which is the integral from R1 to infinity, and we end up with a similar thing. The infinity, of course, the function vanishes, and we end up with this. And if we add the two together, we get the total for the energy of repulsion of the two electrons with this funny symmetrical wave function. And luckily for us, when we take the two of them together, a lot of stuff disappears and cancels out, and we get something a little bit more tractable. We have two terms, minus 1 over zeta 1 squared plus minus 1 over zeta 2 squared, and then a cross term, zeta 1 plus zeta 2 squared, and then a term with 1 over R1 and some rational functions, and then 16 over R1 and a more complicated thing that again has the sum of zeta 1 and zeta 2 cubed. Now we've got this done then. That's the integral over R2. We've now got to integrate this thing over R1, just like we did before with the single electron terms. And that's good because at least it doesn't get any more complicated. Putting this in and putting in the n and everything, we can show that we get this formula here that is not at all obvious and that has been factorized using Mathematica to make it much easier, because if we don't factorize it, we end up with mile-long terms that stretch across a piece of paper, and it's very easy to get lost and lose terms. And this very funny formula here with zeta 1, zeta 2, and then a very big polynomial in zeta 1, zeta 2, you can verify that if you put in zeta 1 equals zeta 2 equals 1, then the top part is 80, and the bottom part is 16 times 8, which is 128, and 80 over 128 just happens to be 5/8. And that's what we got for the repulsion integral when we first did our very first calculation and had just used zeta. We didn't even have zeta, it was just 1. So that means that again, we probably are on the right track here. We've probably got everything working in our favor. Now we've got to take this and two of the other ones, and we've got to add them all up together, and that turns out to be a separate thing, which I've had to put in very, very tiny print here, for which I apologize. And you can verify again, luckily substituting zeta equals 1 for both of them is not too hard to do, that if you go ahead and substitute in for the total energy and put zeta 1 equals zeta 2 equals 1, you get minus 3/8. perfect. Just exactly what we got the first time. So now we've got this magic formula. It seems to be right. Boy, does it look complicated. Now what we are supposed to do is we are supposed to find the minimum of this horrific thing. And the minimum values of zeta 1 and zeta 2 not equal that minimize this thing. And then that will be our final result. That is not at all easy to do, because what we would have to do is we'd have to take the derivative, and this thing has lots and lots and lots of terms, so you can practice the chain rule here till you're blue in the face, plus it's a quotient, so it's the old ho d hi minus hi d ho over ho ho, and it's going to be a giant mess, a really big mess. And therefore, we aren't going to try to even attempt to do this analytically. You can imagine, though, when this kind of thing was being done back in the 1930s, they didn't have computers. And so if you wanted to calculate things out, you had to use a mechanical calculator of some type or calculate things out by hand. So even after you get done and you've got this thing here, it still may be extremely difficult to actually evaluate it. It may take a long time indeed to figure out how to get a decent result. What we're going to do then, instead of differentiating this function, is we're going to plot the function. We're going to plot E of zeta 1, zeta 2 versus all possible reasonable values of zeta 1, zeta 2. We know that zeta 1 and zeta 2 can't be too small, because if they're too small, then the thing's too big. And we know that they can't be too big, because if they're too big, then the orbitals are too small. And we certainly don't want to put in 0, because then we may have 0 in the denominator, and we end up with something that blows up or is very hard for the computer to deal with. So what we're going to do then is pick some reasonable values and plot the contour plot of this and just look at it. Where the contours are low, that's where there's probably a minimum in energy. And because, although it's not obvious from the form of this thing just by staring at it, it is in fact symmetrical in zeta 1 and zeta 2. And so we should see a symmetrical contour plot. It should have symmetry about the 45-degree axis. And if it doesn't, again, that's a clue that we have a bug in the formula. Either when we typed it in to do the contour plot, we might have mistyped a 15 for a 16 or something. Or some deeper result may be, in fact, there's something else wrong, and we have to go back and make sure it's correct. Here, in fact, is the symmetrical contour plot here on slide 485. The red parts are the parts where the energy is low, then going up to purple and blue, and then going through green and yellow, gray and white, where the energy is high. And I think you can see that the energy is high when on the 45-degree angle. The energy is high when zeta is too small. That's because when zeta is too small and you're on the 45-degree angle, both electrons are way out there and they don't have a favorable interaction with the nucleus. If you're too big, then both the electrons are too close and they have a lot of electron repulsion then, and so you get this kind of saddle-shaped function here. And what we got before is right on that purple, the middle purple part. That's the part we got when we only had one possible value of zeta and we took the derivative. We had that simple function there and we got that value. Now, however, what you can see is that if you're willing to go off axis and either make zeta 1 very small and zeta 2 big, or the other way around, which is exactly the same thing, you can get a much better result, because now you can see that it dropped down quite a bit. Looks like one of them is about 0.2 something and the other is about 1 something. And that kind of makes sense, because then one of them is sort of like hydrogen atom, because that would be 1, and then the other one is really floppy, way out there, because why? Well, the one that's inside is pretty much shielding the nucleus charge, and so the other one is very weakly bound. Let's go ahead and zoom in then. I've zoomed in on the upper left here, and by picking values from 0.2 to about 0.6 on the x-axis, and from 0.5 to 1.2 on the y-axis. And now we can see that the center area of that red almost elliptical shape is a little bit bigger than 1 for one of them, and a little bit smaller probably than 0.3 for the other. And now that we see this, what we can do is we can put in values near there, and with a digital computer we can do a search. We can just take all possible values of zeta 1 and zeta 2 on some grid and evaluate this function. After all, that's what the computer did to plot it anyway. And so we can ask it to return the lowest value in just a double loop, and that's very, very quick. That's like the blink of an eye to do that. And if we do that, we find that we have some success. We find the minimum value of the energy functional of zeta 1, zeta 2 is with values of zeta 1, arbitrary, 0.283221, and for zeta 2, 1.03923. And when we put that into that very, very messy formula, these numerical values, which I tried to get out to quite a few digits because I'm raising them to the 6th power and doing things and adding and subtracting them, and I don't want round off to kill me. And it's a pretty good thing that we kept all these digits, because the energy evaluates to minus 0.513303 Hartrees. This is a great success because it's finally less than a half. And so that means that we have a wave function now, perfectly good wave function, and we've shown that, and we know it's not the best one. I mean, that would be a miracle if it were somehow the best wave function we could ever find. We only had 2 parameters, and we didn't really go crazy or anything, but at least by supposing that one electron is inside the other one and then vice versa, and taking that symmetrical combination, it worked. So there was some physical insight. We went from a hydrogen atom to a bigger hydrogen atom to something more realistic, and we finally got the thing to work. So that means hydride anion is slightly stable. It's not that stable, but it's slightly stable. And if we compare the ionization energy of the hydride anion, which is known quite accurately, sadly we find that the true hydride anion is about twice as stable in the sense that it has about twice the ionization energy as what we've calculated. So rather than minus 0.51, it's like minus 0.52 or something like that. That's what the experiment says. And so we would have to think a long time about how to modify our wave function in order to figure out a better value. We'd have to introduce something else in there. Well, what could we do? We could blindly, I would say, we could take 3 exponentials. That gives us more flexibility, but there's no physical motivation to do that. The two exponentials were chosen because we thought one electron was inside the other one. Now we put in 3, it doesn't change the energy much, if at all. I didn't want to do the calculation. That could be extra credit if you want to get into that, because those 9 cross terms are going to be mighty, mighty tedious to deal with. And then who knows if we can even optimize it, because we can't necessarily do a contour plot when we've got 3 variables. It's very hard for us to visualize. So we'd have to basically ask the computer to go ahead and put in all possible values of zeta 1, zeta 2, and zeta 3 within reason, and then see if we got anything. And my feeling is we won't get anything, and so I didn't want to do that. We could, instead of using the orbitals that we used 1s orbitals, and then we made one stretched out and the other one not so stretched out. What if we took a linear combination of 1s and 2s? We could do that. That could have some advantages when it comes to doing the single electron terms, because those are eigenfunctions of the single electron terms, and so we can just write down the energy there. We don't actually have to do, but unfortunately the repulsion term then gets pretty messy, because we have, for the 2s, we have 2 minus r in the integral, and so we can end up with integrating by parts 3 times rather than twice, and so that might not be so easy. That's plenty of work as well. But that could improve things. And a very good way here, I've given you the reference here on the bottom of slide 488. Believe it or not, Hilarius in 1930, with a mechanical calculator, went through this exact thing that we've been doing with a much more involved wave function. Well, I shouldn't say much more involved, but with a different kind of wave function. He picked psi of R1, R2 as some normalization constant, and then he picked e to the minus zeta R1, e to the minus zeta R2. Okay, that part, that was the first one we did. We know that doesn't work. But then what he did is he included a term in the wave function that has R12. So he took 1 plus some constant, c, times R12. What does that do? Well, R12, remember, is the distance between the 2 electrons. That's just the scalar distance between them. What this does then is when R12 is small, it depends what c is, but when R12 is small, the wave function shrinks. Now this is a kind of an automatic. If you include terms in the actual difference distance between the electrons in the wave function, so it's no longer a function of just R1, R2 separate things, but it has R1, R2, which is a complicated formula, then you can control the wave function then so that when R1 and R2 are near to each other, that term gets small, and when R1 and R2 are far away from each other, that term gets bigger. And that in fact gives you a lot of flexibility to do that. And I think if you do that, at least for helium, which is what the paper was about, not hydride, you can get within 0.5% of the correct ionization energy. So you can do extremely well by doing that. And that's the basis for that argument, is that you want to have, you know, the electrons don't like to have the same coordinate where R1 minus R2 is small. And so by putting that in there, you can control it. And you could argue, well, why not put in R12 squared and so forth, and so you can get into a polynomial in R12 if you want to. This gives the energy for helium to 0.5%, as I said, but there is a hidden cost here, which is almost unbelievable when you think that he did this with a mechanical calculator and a very sharp pencil. And the hidden cost of doing this is that now all of our integrals that before were so clean with just exponentials and stuff, they're now clouded up with R12 in there. And 1 over R12 wasn't so easy, and R12 isn't so easy either. And so we end up with all this complication. And so as usual, if you want to adjust the wave function to make it more realistic in these multi-electron systems, unfortunately it gets much, much, much harder. The other thing that chemists don't like by putting in R12 is that now they don't know what's going on. So now I have this thing, the wave function, but I can't think of it in terms of an orbital for the first electron and an orbital for the second. And in fact, even in the function that I picked, that was the symmetric combination, that can't be written as a product of one electron wave functions either. If it could, we could divide through by one of them and we'd get the other, but we've got two different exponentials there. And so that doesn't, that's already a more complicated wave function, that one, than chemists would like to look at. Chemists really like the idea of orbitals where each electron has its own one electron wave function, and then the total function is the product. And they like that even if it's not the most accurate, because it allows them to think and predict what's going to happen and think of which electron in which orbital has a higher energy than another one or something like that, and have some intuition about what's going on. And it doesn't help to calculate a very accurate energy if you then are completely lost when you look at the wave function and you can't actually figure out what it means. So now you've got the answer, you look at the wave function, it tells you everything that you want to know, but it's not telling you what you want to know because you want to have some intuition about each electron, where it is, and not just the total aggregate thing. Therefore, what we are going to do now is go back to the orbital approximation, and we're going to take a closer look at it and how we can systematically do things with even more than 2 electrons if we have to with the orbital approximation. Because if we have 3 electrons for lithium, good luck in including R12 and R23 and R13 and so on into the functional, and then trying to figure out what's going on. That's going to be a very long row to hoe. Instead then, let's write that psi R1, R2 is equal to some function of R1 times some function of R2. And the functions themselves can be anything. They could be hydrogen-like orbitals, or they could be anything we dream up. They can be orbitals with different values of zeta. The key is that you have one and you have the other one, and you have to multiply them together to get the total. You can't just have something else. If you put R12 in there, then it won't separate. That's basically why the whole problem was so messy in the first place, is because R12 wouldn't separate. The question is, what sort of orbitals should we use? And an American physicist by the name of John Slater suggested that what you ought to use should be orbitals that are easy to integrate. This is like looking around a lamppost to find your keys. It's the only place there's any light. And you look for things that are easy to integrate because you're going to be doing a lot of integrals. And so if you have something that you can just go like that and get the answer by looking in a table, that's going to be extremely quick to do. If you are proposing functions that are very messy to integrate or take a long time, then you're going to be spending forever. And he proposed these functions I've written on the bottom here of slide 490 that are often called Slater orbitals. They're sort of like hydrogen-like orbitals with an angular part, but rather than having a polynomial in R where we had the radial nodes, recall, for the hydrogen atom, these functions don't have any radial nodes like that. They're just various powers in R and then e to the minus zeta R and then some angular part if we aren't dealing with an s orbital. Zeta here is just a parameter that we optimize. It isn't equal to the nuclear charge like it should be if we were just dealing with one electron systems. They're convenient to integrate. They don't have any radial nodes. We can use them. They're really common, used in quantum chemistry. And for helium, I've written out here what the best single electron orbital, the single electron wave function, or the 1s orbital for helium. It's pretty well approximated by a Slater term with two terms. So the first term is about 84% Slater 1s orbital with zeta 1.453, and then another 20% or so with Slater orbital with zeta equals 2.910. The other electron orbital for the other particle has exactly the same form of this, and the total for the two of them is the product of these things. And that gives you the best value. Because there are two different values of zeta, then in the jargon, this is called a double zeta orbital. And there are all kinds of jargony terms in quantum chemistry, depending on a lot of things. What kind of potential terms you included, how many interacting particles you allowed in your equations, how big a basis set you chose, and what kind of functions you allowed to be admitted as candidates to get the energy, and so forth. And they're all very important to know if you're in the business, because they're going to tell you how much computational work you're going to have to do. I think you can see that even by what we did by hand. If we take something with more terms in it, the amount of work expands very rapidly, and sometimes it just gets completely unmanageable. Even for a supercomputer to do, it may become unmanageable. It may just take exponentially longer, and we can't wait around that long, because our grant is up for renewal before then. So how well can we do with these orbitals? Well, for the best double zeta orbital, the energy of the helium atom comes out to be minus 2.8617 in terms of Hartrees. For the symmetric wave function that I proposed for hydride, which is not just a product of two orbitals, the energy is minus 2.875, so that's better. But in that one, we don't have orbitals anymore. We just have this symmetrical wave function. For hydride, apparently, based on the orbital approximation, hydride just isn't stable, ever. And so it would be kind of tedious to find that out, I think. And I'm not quite sure myself how that's proven. But if we take two double zeta term like that with hydride and do the same thing, we get an energy higher than minus a half Hartree. So that simple symmetric function is better. However, we wouldn't be able to guess for 3, 4, 5 electrons and so forth what's going on. And hydride's kind of a special case because there's only a single charge and there's 2 electrons and so on. And so for other atoms, we're going to get pretty accurate results by looking at these orbital approximation, and we don't necessarily have to trouble about the fact that it's not super accurate, because we can make it pretty accurate. The question is now, how do you solve these equations if you've got 2, 3, 4, 10, a barium atom? And I'll close this lecture by this picture of Douglas Hartree. He met with Niels Bohr. His advisor was Professor Rutherford, and he was very good in math, and he was very interested in this new theory of the atom that Niels Bohr had come up with that was eventually superseded. The Bohr model of the atom explained some things by quantizing angular momentum, saying it had to be in units of h bar, and that explained some of the energy level dependence, but ultimately was shown to be incorrect. And the correct theory, of course, is the Schrödinger equation, which gives everything correct. He devised a method that was then modified by a Russian, Fock, and together it's called the Hartree-Fock Approach. And it's something that you have to know about if you're going to get into anything about calculating these energies, because it's by far the most commonly used method, at least to start with when you're looking at these systems. And it's an extremely clever method because it gives you some physical motivation for what you're going to do. And then on top, which is very important, it gives you a numerical procedure with a well-defined stopping criterion for calculating the energy and when you should stop. And I'm going to pick this up next time by taking the probability distribution of one electron, and rather than having the real live electron there with the first one buzzing around like two flies, I'm going to take one electron and I'm going to smear it out into just its own charge distribution. And then I'm going to let now it's not alive anymore, it's dead. It's just a static charge distribution. And then I'm going to let the first electron interact with this static charge distribution and with the nucleus. And then I'm going to try to solve for the real live wave function of the first electron. And then I'm going to have to figure out how to improve my solution. So we'll pick it up from there with this nice picture of Douglas Hartree staring at us from the past.